There is a machine traveling through the darkness of space right now, farther from Earth than any human-made object has ever ventured, sending back signals that are rewriting everything we thought we understood about the boundary between our solar system and the stars beyond it. 48 years after its launch, Voyager 2 has crossed a threshold that only one other spacecraft has dared to approach. What it's finding there is challenging the very models we use to understand our place in the cosmos. To understand what Voyager 2 is discovering, you have to first understand what it was sent to do and where it has traveled. In 1977, during a rare alignment of the outer planets that occurs only once every 176 years, NASA launched 2 spacecraft with an audacious mission to explore Jupiter, Saturn, Uranus, and Neptune before leaving the solar system forever. The scientists who conceived of this mission knew it would take decades. They built the spacecraft to last 20 years, but they hoped they dreamed that it might somehow survive far longer, continuing to transmit data from the vast emptiness beyond. Nobody dared say it, but they were hoping Voyager might reach the edge of the known universe itself. The spacecraft were named Voyager 1 and Voyager 2, and they became the most resilient machines humanity has ever built. They encountered storms and radiation and the crushing forces of gravity near the largest planets in our solar system. They transmitted stunning photographs and unexpected discoveries back to Earth, thrilling scientists who waited in control rooms for signals that took hours to arrive. Voyager 1 and 2 revolutionized our understanding of Jupiter with its raging storms and complex moon system, revealed the stunning ring systems of Saturn, and discovered entirely new moons and atmospheric phenomena at Uranus and Neptune. But the scientists behind the mission knew that the real adventure was just beginning. Once the planets were mapped, the probes would leave our solar system and drift into the interstellar medium, the space between stars. For decades after leaving the outer planets, the Voyagers traveled through what seemed to be emptiness. But they were not traveling through nothing. Around the sun, extending billions of miles into space, is a bubble of protective envelope called the Heliosphere. Inside this bubble, the sun's influence dominates. Radiation streams outward, its magnetic field extends far into space, and its solar wind, a constant flow of charged particles, pushes against everything around it. This was the domain of the solar system. Beyond it lay something unknown, something fundamentally different. The boundary between the heliosphere and interstellar space is called the heliopause. For decades, scientists could only theorize about what it would be like. Would it be a sharp border or a gradual transition? Would there be a shock wave where the solar wind collides with the interstellar medium? What would the temperature be? What kind of particles would be found there? How strong would the interstellar magnetic field be? These questions haunted space physicists. Nobody knew. The only way to know was to send machines to measure it directly. Voyager 1 crossed the heliopause first in 2012, triggering excitement throughout the scientific community. For the first time, humanity had a spacecraft beyond the sun's influence, sending back data from the other side of that invisible boundary. Scientists held their breath as the data arrived. What they discovered was both fascinating and puzzling. The density of the interstellar plasma was higher than expected. The temperature was different. The magnetic field had an unexpected structure. Each discovery raised new questions. Voyager 1 was still operating, still sending data, but it was showing signs of age. Its power systems were degrading. Its signal was becoming fainter. Then, in November 2023, Voyager 2 crossed the heliopause. And when the data started arriving, scientists began noticing something remarkable. The conditions Voyager 2 was encountering were significantly different from what Voyager 1 had found. The solar wind density was changing in unexpected ways. The interstellar magnetic field had features that contradicted existing models. The temperatures and particle compositions suggested that space itself at the boundary of our solar system was far more complex and dynamic than anyone had predicted. Not an alien signal or a hidden planet, but something far more profound. The realization that our most sophisticated models of the universe's structure might be incomplete. To understand why this matters, you have to grasp what the heliopause is, and why crossing it is so significant. Imagine a ship sailing through an ocean. The ship creates a wake, a disturbance in the water behind it. The sun, moving through space, creates something similar, a bubble of influence in the sea of interstellar material. This bubble is the heliosphere. The solar wind blows outward from the sun, carrying its magnetic field, its particles, its influence. But as it travels farther from the sun, it loses energy eventually. It meets the interstellar medium, the material between stars. Consisting of neutral hydrogen atoms, helium, dust, and the magnetic fields that permeate all of space. At the boundary between these two regions, something dramatic happens. The solar wind, traveling at hundreds of kilometers per second, crashes into the interstellar medium. This collision creates a shock wave, a sudden increase in density and temperature and pressure. This is the heliopause, and crossing it means leaving behind the sun's protection and entering a completely different environment. It means encountering particles and radiation that have never been influenced by our sun. It means finding out what the space between stars is really like. When Voyager 1 crossed the heliopause, scientists got their first direct measurements. But when Voyager 2 crossed, 11 years later, at a different location in space, the measurements were subtly, but significantly different. The solar minimum that Voyager 1 crossed the boundary during a particularly quiet period of solar activity. Voyager 2 crossed during a more active phase. This difference in solar activity meant that the two spacecraft were experiencing different conditions at the boundary. One probe's data wasn't enough. With two probes at two different locations, scientists could begin to map the three-dimensional structure of the heliopause. And what they found was stunning complexity. The interstellar medium is not uniform. It has structure. It has variations. It has asymmetries. On one side of the sun, the pressure from the interstellar medium seems stronger. On another side, the magnetic field has a different configuration. This suggests that our solar system is not simply parked in a static ocean of interstellar material. It's being buffeted by currents, pushed by winds, influenced by the irregular structure of the galaxy around it. The sun's bubble, which we had imagined as relatively stable, is actually being deformed, compressed, and shaped by forces we are only now beginning to understand. The discovery became even more intriguing when scientists began comparing Voyager 2's data with observations from other sources. The Interstellar Boundary Explorer, or IBEX, is a spacecraft that orbits Earth and observes the boundary of the solar system indirectly. This discovery has direct consequences for our understanding of cosmic rays. These are the highest energy particles in the universe, traveling at nearly the speed of light, arriving at Earth from distant source, supernova, black holes, neutron stars, and other violent cosmic events. Cosmic rays carry crucial information about the universe's most extreme environments. But they don't reach Earth's surface in full force because of the heliosphere. The sun's magnetic field deflects them. The solar wind provides protection. Understanding the heliopause means understanding how well the heliosphere shields us from cosmic radiation. And now, with Voyager 2's data suggesting a far more complex boundary region, scientists must reconsider the nature of that protection. There's something else hidden in the data that has scientists particularly intrigued. Voyager 2's plasma wave instrument has been detecting unusual fluctuations in the interstellar medium. These are waves in the plasma solations that propagate through the ocean of charged particles beyond the solar system. Where are they coming from? What is causing them? One possibility is that they are generated by the collision and interaction between the solar wind and the interstellar medium at the heliopause itself. Another possibility is that they are manifestations of turbulence created by the sun's motion through space. The sun is not sitting still. It is orbiting the galactic center, moving through the interstellar medium at about 20 kilometers per second. As it moves, it creates a kind of bow shock, similar to the bow shock created by a ship moving through water. This realization led researchers to an even more speculative, but scientifically grounded, hypothesis. If the sun's motion through space creates turbulence and waves in the interstellar medium, then the structure of the heliopause might be asymmetrical. The side facing the direction of the sun's motion might be compressed and shaped differently than the trailing side. This could explain why Voyager 1 and Voyager 2, despite crossing the heliopause at different times and in different locations, are encountering significantly different conditions. The boundary between our solar system and interstellar space might be like a comet's tail, asymmetrical, dynamic, flowing. For the first time, we are beginning to map not just where the boundary is, but what it actually looks like. What makes this discovery even more profound is that it forces scientists to confront a humbling truth. The models we had built to describe this region were based on limited information. We had theoretical predictions, but we had only one data point, Voyager 1, from the actual boundary itself. The arrival of Voyager 2 with different data shows that reality is more complex than theory predicted. This is not a failure of science. This is exactly how science is supposed to work. Theory makes predictions. An experiment tests those predictions. The experiment reveals unexpected complexity. Scientists adjust their understanding. Then they develop new theories that better match reality. Extending the Voyager's lifespans decade after decade. Every year that passes is a miracle. Every new data transmission from the edge of interstellar space is a victory against the unforgiving environment of space itself. Voyager 2 carries a golden record, a message from Earth encoded on a phonograph record made of gold-plated copper. This record contains photographs of Earth, greetings in 55 languages, music from cultures around the world, and the sound of human heartbeat. It was placed on the Voyager spacecraft in case the probe ever encountered extraterrestrial life. The message says, in essence, we are here, we exist, we reached out across the vast distances of space to say hello. That message is now beyond the sun's influence, traveling into territory where it will outlast our planet, our species, and perhaps everything we have ever built. It is the most distant artifact of human civilization, a time capsule traveling through eternity. But the Voyagers are not just time capsules. They are scientific instruments. They are eyes and ears that extend human perception. Billions of kilometers beyond Earth, every measurement they take, every data point they send back, helps us understand the universe better. The discovery that the heliopause is far more complex than we expected is not a final answer. It is a new question. It is an invitation to send more probes, to design better instruments, to develop more sophisticated theories. It suggests that the boundary of our solar system is not a simple fence, but a complex frontier, a place where two fundamentally different realms collide and interact. Scientists are already discussing the next generation of interstellar probes. Unlike the Voyagers, which are powered by radioactive plutonium running down like dying batteries, new spacecraft could be powered by solar sails, by antimatter engines, by nuclear propulsion systems, or by technologies we haven't yet conceived. These probes could carry better instruments, could operate longer, could venture even farther into interstellar space. They could measure the structure of the interstellar medium over larger distances, could help us understand the three-dimensional architecture of the galaxy around our solar system. They could reveal whether the complexity we are seeing at the heliopause exists throughout interstellar space, or whether it is unique to our local region. And as these probes travel farther, as they collect more data, as our instruments become more sophisticated, we will be answering a question that has called to humanity since we first looked up at the stars. What is out there? The answer, it turns out, is far more complex and wondrous than we ever imagined. It is not a realm of simple emptiness, but a place of intricate structure, dynamic processes, and hidden complexity. The space between stars is not empty. It is alive with particles, sculpted by magnetic fields, shaped by the motion of stars through the galaxy, filled with processes we are only beginning to understand. Voyager 2, now 48 years old, continues its journey into this mysterious realm. Its signal takes 14 hours to travel from the edge of our solar system back to Earth. That signal is faint, the equivalent of a cell phone transmitting from the distance of Neptune, yet scientists are still receiving it. They are still listening. And every few seconds, that faint signal carries information about a region of space that no human has ever visited and no human likely ever will visit in our lifetime. It is the closest we may ever come to touching the true boundary between our solar system and the stars beyond. What Voyager 2 has discovered is that this boundary is not what we thought. The sun does not create a perfect bubble of influence with a clean, well-defined edge. Instead, the heliosphere is shaped and deformed by its motion through space, compressed and buffeted by the irregular structure of the interstellar medium, filled with waves and oscillations that we are only beginning to detect and understand. The solar system is not an island sitting in a static sea. It is a dynamic system, constantly interacting with its environment, shaped by forces that extend billions of kilometers from the sun. And this leads to a realization that might be the most profound of all. If our solar system's boundary is far more complex than we thought, then every star system in the galaxy probably has an equally complex heliopause. Billions of stars, each with its own bubble of influence, each interacting with the interstellar medium in unique ways, each shaped by its motion through the galaxy. The galaxy is not empty space scattered with stars. It is a complex, interconnected system where every object influences everything around it. We are not observers standing outside the universe looking in. We are part of it. Our solar system is embedded in a dynamic, evolving, endlessly complex cosmos. Voyager 2 will continue to transmit data as long as its power systems survive. Estimates suggest it might keep sending signals for another decade, perhaps longer if engineers can keep it alive with clever power management. Eventually, the last of its radioactive plutonium fuel will decay. The spacecraft will fall silent. It will become a ghost ship still traveling outward, still moving beyond the heliopause, still carrying humanity's golden record deeper into the unknown. Centuries from now, long after our species has evolved or disappeared, long after Earth has been consumed by the aging sun, Voyager 2 will still be traveling. It will be the last evidence that we existed, the last message from a world that dared to send machines to touch the edge of infinity. But for now, while it still lives, while it still sends data, Voyager 2 continues to teach us. It shows us that the universe is stranger, more complex, and more wonderful than we imagined. It reminds us that there is still so much we don't know. And it whispers to us across the billions of kilometers of empty space. Keep looking, keep wondering, keep reaching outward. The answers to the greatest mysteries are still out there waiting to be discovered by the next generation of explorers, the next wave of spacecraft, the next chapter in humanity's journey to understand our cosmos. The edge of the solar system is not the end of the story, it is only the beginning.